Okay. We can describe the proportions of the reactant and product in an equilibrium by writing something called an equilibrium constant. Right? So this is kind of just getting to what she was saying. You might think, just from looking at that equation, that when it reaches equilibrium, you've got equal amounts of NO2 and N2O4, but that's not necessarily the case. And so the way that we describe quantitatively how much of each there is when the reaction reaches equilibrium is to write this thing called an equilibrium constant. And that has the symbol of big K. K for constant. Yeah?
Same as K for Kelvin.
This is italicized, though. It's a subtle difference. I mean, you're right. There's only 26 symbols you can have, plus, well, if you're physics, then about another 15 for all the Greek letters, and then you run out. So, yeah, lots of things get, like C for concentration, C for speed of light. You would think people wouldn't get those confused, but you'd be surprised. Okay, so the equilibrium constant K. For our equilibrium that we're talking about, NO2 in equilibrium with N2O4, the equilibrium constant expression looks like this. Right? So the K, now as I'm going to emphasize endlessly on the next slide, the K is a number. But that number is equal to the ratio of the concentrations of your reactants and products when the reaction reaches equilibrium. Right? So you have your NO2 and you do the reaction and it starts turning into N2O4, and then at some point it reaches equilibrium and the concentrations of NO2 and N2O4 no longer change. The reactions are still happening, but the concentrations don't change anymore. At that point, if you can go in and measure what those concentrations are, then those are the numbers you put in here. Right? So on the top, we have the concentration of the product, the thing on the right-hand side, the concentration of N2O4. The square brackets are a shorthand way of saying concentration. Right? At school, maybe you've got a little C with the brackets. Here, the square brackets mean concentration. And note that at the end, I've got a little E. The little E stands for equilibrium. Can I please encourage you to get into the habit of writing little E's? You may not have seen this before. Did any of you at school get taught to do a little E there? No. Never mind. Do a little E. That indicates it's the concentration of that thing at equilibrium. This will be much easier for later on when we're talking about concentrations of things that aren't at equilibrium. Then you can distinguish between them when you're doing all your beautiful working in your problem solving. Yeah? So the concentration of the product, which is N2O4 at equilibrium, divided by the concentration of NO2, the reactant, at equilibrium, and note that that bottom concentration is squared. It's squared because there's a 2 in the balancing here. Right? So if there's a stoichiometric coefficient in front of one of the species, that turns into an exponent in the equilibrium constant expression. Right? So there's nothing here, so there's nothing here, but here there's a 2, and so this concentration here becomes squared when we're working out the value of the K. Yeah? Yeah, in the tutorial today we're going to get lots of practice at writing these equilibrium constants. There's various rules, and I can't remember how many of the rules we talk about in the lectures, but if we don't cover them, you'll cover some more stuff in the tutorial. Yeah? And so in general, this is a nice summary of it. Sir?
How do you decide which ones are about the following?
You assume that you are living in a Westocentric culture where everything's written left to right. Yeah? And so left means reactants, so they're on the bottom. Right means products, they're on the top. If you turn the reaction round, the equilibrium constant gets turned upside down, and the value of the K is different. Right? So it's important to know which way the equation's written. because the K will be for that reaction as written, assuming that left to right is reactants to products. Yeah? Okay, so here is the thing, the little story, and one of the lecturers who, yes, you may well get in first semester, dear old Lyle, he has a wee song that is what he calls Lyle's Litany, which is like this little chant that he gets the class to do to sort of remember this. But basically, the equilibrium constant expression is the equilibrium concentrations of the products, each to the power of their stoichiometric coefficients, divided by the equilibrium concentrations of the reactants, each to the power of their stoichiometric coefficients. Yeah? Which sounds a bit of a mouthful, but it's just kind of what we just did in the example previously. Right? So the products go on the top, and if there's a big balancing numbers in front of the products, they turn into powers or exponents on those concentrations. And the reactants go on the bottom, and again, if there's stoichiometric coefficients for them, they turn into exponents or powers on those concentrations.
Is that also the same if you're getting more, like if the reaction's going more the opposite way?
Yes. Yeah.
So did you say do you turn the equation?
No. If you wrote the equation down the other way around,
Yeah.
then the thing on the left is always the thing on the bottom, right? So if you turn it round, then that goes on the bottom, and so the value of the K is different, but it's for a different reaction, subtly. Now, part of the thing about these is that we're putting in numbers that correspond to concentrations. And what we said yesterday is that concentrations correspond to an amount of something dissolved in a volume of something else. Now, that kind of implies that you can't have anything for solids in an equilibrium constant expression, because a solid doesn't have a concentration. Yeah? It isn't an amount of something dissolved in something else. In the same way, you don't put in a pure liquid, which in theory could be lots of things, but in reality is water, because it's the only one you're going to see. So you never put pure water into an equilibrium constant expression, because there isn't really a concentration for that. I mean, there is, but what in fact happens is that you don't put the pure water in, right? So no solids, no pure water, so H2O brackets L. And the other thing, just in case you're starting to get worried, is that what we tend to do is we tend to put gases in, like we just did with the NO2 and the N2O4. And the way we think about that is we think about the concentration of the gas as being an amount of gas in a certain volume of container, right? So imagine we have 1 mole of NO2 and we have it in a 1 litre flask, then we would say that its concentration is 1 mole per litre. Not 1 mole of gas per litre of solution, but 1 mole of gas per litre of container. Yeah? That's a bit of a fiddle, but in order to not do the fiddle, we have to teach you a whole bunch of other stuff which is no longer at school. Something called the ideal gas equation. Some of you may have come across that in physics or something. We don't do it at school anymore in chemistry. We don't do it in first semester chemistry. We do it in second semester chemistry. But by then, you already hopefully know what a K is. So we tend to do this sort of shortcut when it comes to gases, and we just talk about gases in moles per litre as well. Right? But we don't put solids in, and we don't put H2O liquid in either. Now, K is a number. The equilibrium constant expression is this little thing we've just been doing with the ratio of the concentrations, but the K itself is a number. And what's more, the value of K, this number, for a particular reaction is constant. Hence the name equilibrium constant. So unless you change the temperature, that value of K applies regardless of the amounts or the concentrations of stuff that you start with in your reaction. When it reaches equilibrium, regardless of what those actual concentrations are, that ratio of them will always equal that number. And this seems to be another thing that people never quite get along the way. The K is a number and it's a constant. And so you might already be thinking, well, I'm sure I can come up with some way mathematically that I can make it not work. If I have really crazy concentrations and stuff, it won't work. It will always work. I believe the guy who worked this out won a Nobel Prize at least 100 years ago, so no one's disproved it yet. So it is right. It will always work. So, if we can have some reaction which is at equilibrium, and we can measure what those concentrations are, then we can calculate what the K will be. So, for example, here's our NO2 one that we've been talking about. Let's imagine we've taken some amount of NO2 and we've put it in our flask and we've done whatever we need to do, and now the reaction's at equilibrium, and we can go in and we can measure the concentrations. And let's imagine that the concentration of NO2 gas at equilibrium was 0.056 moles per litre, and the concentration of the N2O4 at equilibrium was 0.013 moles per litre. Given those values, we can work out the K like this. We just have to write out our equilibrium constant expression first. Equilibrium constant equals the concentration of N2O4 at equilibrium divided by the concentration of NO2 at equilibrium squared. And then we just plug in the numbers and we work it out. And so in this case, it comes out as being 4.14. And so what I'm telling you, yes?
Do you not square this one?
No, because the top one has no 2 in the balancing. You mean up here? This one?
No, square the bottom. You just square the bottom.
Yep. And so 4.14 is the value for the equilibrium constant for this reaction at some temperature. Now that's not specified there. Let's imagine it's room temperature. Then that will always be what you get when you measure equilibrium concentrations of those two things for the reaction at equilibrium. Regardless of how you set up the reaction, regardless of how much NO2 you start with, regardless of how much of everything you've got there, when it's at equilibrium, that ratio will equal 4.14. Right? Because it's a constant. It says at the bottom, note that K has no units. This is kind of the way it's done at school, and it's kind of the way that it's pretty much everywhere done at first year chemistry. If you go on and do second year, then you start worrying about units for Ks. Right? Because strictly in these things you're not supposed to use concentration, you're supposed to use something called activities. And it's all more complicated than it needs to be right for the moment. The idea is the same, it's just mathematically a bit more involved. So Ks never have units. Okay, we happy? Yeah? Note that the size, this is what we were talking about, note that the size of the equilibrium constant gives us an idea of what we call the position of equilibrium. So let's imagine a little sort of equilibrium of compound A being in equilibrium with compound B. And so for that, we could write an equilibrium constant expression that the K would just be the concentration of B at equilibrium over the concentration of A at equilibrium. Right? That's nice and straightforward. And then let's imagine what the K is going to be if the values of A and B are certain things, right? And what I'm going to do here is something which I would encourage you, if you're not sure about how these things work, and it's not just, oftentimes you find it's with equilibria, but it can be with other things as well. What we're going to do here is we're going to imagine making B a number and A a number and working out what K is, and then changing A or changing B and seeing how it changes K, right? So you can just do this on your calculator. You don't have to know the numbers, you just make up numbers, but what you want to do is you want to change the numbers and see what effect that has on the K, right? And as we're going to see, because we're going to do lots of lectures on equilibria by the end, this is kind of, I find, a really helpful way to try and keep track of what's going on. So let's imagine that when the reaction reaches equilibrium, there's mostly products and hardly any reactants left. Okay, so if you like, it's like this, with my big arrow on the top pointing that way and a little arrow on the bottom pointing the other way. So when it reaches equilibrium, it's mostly this and not very much that. That's going to make the concentration of B a much bigger number than the concentration of A. Yeah? So the number on the top of our equilibrium constant expression is a big number, and the number on the bottom is a small number. It doesn't matter what those numbers are, and like I say, if you wanted to sort this out in your head, you could imagine that B is 1,000 and A is 1. Okay, that would be fine. It doesn't matter what the numbers are, so long as the number on top is much bigger than the number on the bottom. And if you work out that ratio, you'll work out that K ends up being a big number, right? Much bigger than 1. Obviously, if at equilibrium you had equal amounts of A and B, then the K would equal 1, yeah? Because the concentration of B would be the same as the concentration of A, and so the ratio of those two numbers, if they're the same as each other, would be 1. Yes?
Is a small K less than 1?
Yes. So if the number on the top is very big, and the number on the bottom is very small, indicating that the position of equilibrium is very much to the side of the products, then the K will be a big number, bigger than 1. Right? And sometimes they can be very big. You know, 1,000 is fine. Sometimes they can be 10 to the 40. They can be big numbers, right? Depending on which reaction you're talking about. Hello?
Aren't the current products on the bottom side the opposite equilibrium? So
Yes. No, but the point is that if it went to completion, then the concentration of products would be 0. Yeah? For this to work, there has to be a concentration of reactants so that you've got a number to put in. The question is, sorry?
How do you know what side looks like the product number on? Because wouldn't they be on both sides?
What you do, you mean if it's going both ways, then both of them are a reaction and both of them a product. You go with the way the reaction's written on the page. Okay? Sorry? If you were doing the reaction, then the reactant would be the thing that you started with, right? The thing you got off the shelf and put into the reaction. If it was already at equilibrium, so say you just walked into the room and suddenly you came upon an equilibrium a reaction at equilibrium, and you didn't know how it had got there, then it would be up to you, I suppose, to work out which way suited. But often what you're going to find is that we're going to give you the K and give you the value of the K and get you to do calculations using that. and that K will be for a specified reaction, right? Because like we've been saying, if it was really B going to A, then the K would be a different number to the one that you have for A going to B. Yeah? So if it's mostly products and hardly any reactants when you reach equilibrium, then K is going to be a big number, bigger than 1. And the opposite applies if when the reaction reaches equilibrium, hardly any of the reactants have turned into products, and so the concentration of reactants is still very big, and the concentration of products is very small. Then you have a small number on the top, and you have a big number on the bottom, and so the K ends up being a number much less than 1. And again, you can get equilibria where the value of the K is 10 to the power of negative 25, right? Really, really, really small numbers. And everything in between, okay? It depends on the reaction you're talking about, and to a lesser extent, it depends on the temperature you're doing the reaction at. Yeah?
What if you've got a more complex reaction where you've got like more than 2 reactants?
Same applies.
But like, how do you do the actual concentration calculations? Because if they've got like different stoichiometric coefficients,
Yep.
do you add them together or?
You multiply them together. Yep. I think probably we're going to get to one of those. So it would be A, so it was A plus B, 2A plus B gives C. Then on the bottom it would be A concentration of A squared times the concentration of B. Yeah. Okay, actually there isn't one there. Maybe we'll just do one quickly on the board just to show you that. Okay. Oh, well, let's do this one. This isn't really an equilibrium reaction, but we saw it yesterday. Oh, except, oh no, we can do that. No. Okay. So we saw this yesterday, yeah? We're doing the calculations. Let's imagine now that I do that. What will that be? Okay. So we're going to put the products on the top, yeah? And we're going to write concentration terms for each of the products. Even though one of them's a gas, we're still going to treat that as a concentration, yeah? So up here, hopefully you have written concentration of CO2 at equilibrium, right? Little e. Please get into the habit of doing the little e's. Humour me about this. And then we put the water. No, because it's H2O liquid, and you never put H2O liquid in one of these equilibrium constant expressions. All right? So then we've got the CaCl2, we put that in.
So does the water just disappear?
Water just disappears. Yep. If you want to know where it disappears to, you can ask me later, I can tell you. But it doesn't completely disappear, but we don't do it in here. Yeah. So here's CaCl2 at equilibrium, right? And then on the bottom, what do we put on the bottom? The HCl squared. And we don't put the calcium carbonate, yeah? Because it's a solid. And you don't put solids in either. This thing on the top, I haven't drawn anything, but that's times. Right? If it was plus, you would have to write the plus in to be clear. If there's no symbol written in, then you can assume that you're multiplying those together. Okay? And so that's how you do that one. And then if you could go in and work out those concentrations, when it reached equilibrium, assuming it did, then you could work out the K. And of course it follows that if you knew that and you knew that, and you knew the K, then you could work out this. Yeah? And so that's where a lot of the questions and this sort of thing come from. Not so much us giving you all the concentrations and asking you to work out the K, but giving you the K and some of the concentrations and getting you to work out the other ones.